Okay, so recall, and again, maybe you don't have to jot all this down because, again, you guys did pretty well at the website. So um, typically solids, as temperature increases, you're able to dissolve them better. So for example, when I made the blue dye solution that you're working with today, that was a solid. And some things are able to dissolve more because solubility, the ability to dissolve at a higher temperature. However, this is not something that is just a mathematical thing that you can do right away. So instead, we have to have experimental data to support this. How do they figure out these things? We actually did this once in Chem 1 with potassium nitrate, I believe, where you heat up a solution, so water with a solid, until it all dissolves, and then you cool it. And once it starts to cool, once it reaches that saturation point where you cannot dissolve anymore, it starts to crystallize or precipitate. It kind of looks like a snowball. So this is what we did in Chem 1 to try to figure out solubility for potassium nitrate. We did a little class activity with it. By the way, that technique is called fractional crystallization. I bring this up, maybe not so much because of this right now, but we have talked about different ways to separate out mixtures so far in this unit. For example, was it 2 class periods ago, we did paper chromatography. So remember, some colors, which are different dyes, different molecules, were able to carry up the paper further than others. That was based on polarity. On that same day, you did a packet with fractional distillation. So to distill means you take usually a couple of different pure liquids that are mixed together and you heat them up to get them to evaporate. And then one cools, you separate them out based on polarity. Fractional crystallization is not dealing with separating based upon polarity, but it is separating components. Where if I gave you 2 different ionic solutions mixed together, you could separate them out by cooling it down until one of them undissolves first. Quite frankly, if you remember the Chem 1 semester project at the end of the year, we had you do precipitation reactions in order to separate things out. I mean, if we gave you an ice bath, you might have been able to separate some of the things out just by doing this technique instead. So it's not on our goal sheets for this unit. This one in particular was not mentioned, unlike distillation was mentioned and paper chromatography was mentioned on one of the goal sheets. However, that idea of separating by different means is something that I think is worthwhile to be aware of. Maybe through one slide here. Okay, I get more NyQuil tonight too. That bottle's been cashed. If you become a pharmacist, you learn that NyQuil really doesn't do anything for you. It's a whole bunch of stuff they threw together. However, it works. In particular, the Benadryl. The Benadryl is good. Anything to get you to sleep. We go already? Okay, now gases typically have the inverse relationship. And this was on, I believe, the website. And again, everyone did well on the website. So gases are actually more soluble at lower temperatures. I think the best explanation for this is that when you have a gas, typically it's nonpolar. Nonpolar is not very soluble in, let's say, water, which is polar. The only attraction that they have is dipole-induced dipole. And because of that, the slower the things are moving, the more likely that attraction can take hold. Again, if you were to open up a soda, you want it to be in a cold environment then if you want it to stay carbonated. Heck, second example. Do you like to go fishing in the summer? The deeper the water, the colder it is. It's further away from the surface where the sun is shining down. Hopefully that seems reasonable to you. Well, that's where the bigger fish are. And it's not just because they need more water to swim. It's because bigger fish need more oxygen. And there's more dissolved oxygen lower under the water than there is higher at the surface. because the colder it is, again, the more you can dissolve these gases. So gases inverse relationship, something to be aware of that particular phenomenon as well. Now this is really the main text for this first batch of notes because, again, my next slide is just a reminder of the solubility curve, which you guys were hopefully able to navigate fairly well. But remember, the line represents the saturation point, and saturation is based upon the compound and the temperature. And as you notice, most things increase in solubility as temperature increases. However, there's no set pattern. I mean, the slope for sodium nitrate is significantly different than sodium chloride here. So there is no exact rhyme or reason that I'm aware of what leads to the shape of this graph. But understand that below the curve is unsaturated. Above the curve, if it were all dissolved, would be supersaturated. We actually spent a fair amount of time in Chem 1 going over solubility curves, more than we're going to go over in this class, because it's not nearly as much of a point of emphasis in this class as it was in Chem 1. However, I want to remind you of solubility curves. The last thing I want to go over, which I don't think you need to write this down for, is Henry's law is dealing with the solubility of gases. And what it says is that the gas solution is proportional to the pressure. So what I mean by that, this equation you don't have to know. However, what would be important or noteworthy if you want to jot anything down is Henry's law is dealing with atmospheric pressure, pressure outside. And if I opened up that can of soda, if there's a higher pressure outside, that can keep a higher concentration of the solution. That's what this mathematical expression is trying to show, is that pressure and concentration are directly related. Think about it. If there's a higher pressure outside pushing down on my glass of soda, it's harder for those bubbles to escape. Because, again, how do those bubbles escape? Their vapor pressure has to balance out with the atmospheric pressure. If there's greater push down on the solution, that means those bubbles are not going to escape very easily. However, if there's a smaller push on that solution, those bubbles would escape easily. This is where, if we had a little more time today, what I sometimes do is I bring out the vacuum pump and I open up a soda and I put it in there. I have someone take a drink before and then after, and they can tell that the soda has gone pretty flat. And you can actually see the bubbles rise up very quickly, because if there isn't a push down on the solution, it's not going to allow those bubbles to stay in. The bubbles will just rise very easily at that point. So, like I said, this was meant to be the quick notes on solubility. We did have that worksheet from last time dealing with solubility. What I'd like to do right now is pause this for a second. We're going to divide our notes on light into two parts. Today is going to be more of the concept behind it, which you picked up on the way in, the spectroscopy and the electromagnetic spectrum sheet. And it talks a little bit about light in those as well. So that's what I want to cover today with the notes. Next class, we're going to cover the mathematics of notes, of light, to wrap things up there. So remember wavelength, frequency. Amplitude is not one that we really cover much in Chem 1. Or, for that matter, in AP Chem. Amplitude is referring to kind of the height of that wave. I think physics covers that a little bit better than I do. In chemistry, we're more actually concerned about wavelength and frequency. The symbol for wavelength is lambda. That's what I have up on the board next to my drawing here. Remember, a wavelength is the length of one wave. I mean, it's not a tricky term. That could be from one peak to one peak, like I've shown on my picture here. That could be from one trough to one trough. So bottom to bottom. That could be starting in the middle, an up and a down cycle altogether. Frequency, again, how often the wave occurs. In Chem 1, we would talk about things with a long wavelength have a low frequency. They don't happen very often. High frequency is a short wavelength. Those would be higher energy forms of light. So another thing we have to talk about today is these different types of light. Right? I don't think you had to write the word term, so there's 3 words in the slide. All right, so remember, visible light was 400 to 700 nanometers, roughly. I mean, it might be a little over 700 at times. That's our red, orange, yellow, green, blue, whatever indigo is, and violet. So our Roy G. Biv. There's a low energy form of invisible, which we're going to talk a little bit more of here in a minute. And there's high energy invisible forms of light. And the lowest is radio waves. Then we have microwaves and infrared. Even radio and microwaves sometimes overlap a little bit in their kind of what wavelength is what, but those are long, low energy waves. High energy like UV, X-rays, and gamma rays. And hopefully that is reviewed from Chem 1 as well. And I have one slide to go that's going to talk a little bit more about some of these specific invisible forms of light. The ones that are mentioned on your goal sheet for today. Okay? So, remember what happens is energy excites electrons. Electrons jump up. If they fall back down, they can give off a different form of light. So, first off, my first bullet point is for low energy, kind of like a microwave. And again, I'm taking this right from your goal sheet, because this is something that I've seen them bring up recently. This is one of the newer things that they decided they want to assess students on, and I want to make sure, besides just on that goal sheet, that you have this now spoken to you in class. Microwaves are a low form of energy. This is enough to rotate bonded atoms in a molecule. What that could mean is something as simple as if you had carbons bonded together and you had one chlorine pointing up on one carbon, rotation could cause it now to point down. Think about like 90-degree angles, sp3 hybridized, tetrahedral. Any of this ringing a bell? Carbon bonded to four things, maybe one of those is another carbon. So if you have a two-carbon chain and a chlorine's pointing up, rotation could cause it to go down. So it's not just in one fixed position. That's enough energy to kind of move things about within the molecule, to make things rotate. Infrared is a higher form of invisible light. Now the way that I remember that is in the word infrared is the word red. Red is the lowest energy of the visible, so sometimes that's a good reminder, just like ultraviolet is next after violet. Infrared causes vibration. Vibration causes heat. If you ever heard of infrared goggles, they can see the heat signature of things. Lexi, you ever watched the movie Predator? You should. Predator sees in infrared. Makes him very difficult. Arnold Schwarzenegger had a hard time trying to destroy him. I believe it was in the Amazon. So infrared causes things to vibrate. Ultraviolet excites electrons to transition energy levels. Visible light does the same thing. Although, if that UV gets a little too high, because there's even a scale on UV, it can cause electrons to get excited so much that they jump up and they can't fall back down. Because if you jump too far away from your positive nucleus, there's no longer an attraction to bring you back together. And it's especially true once you get to X-rays. In photoelectron spectroscopy, remember those graphs with the peaks we did last unit? Kind of related that to ionization energy, energy needed to remove an electron from wherever. Well, they're zapping atoms with X-ray level photons. That's enough to excite those electrons, get them to jump so high that they can't come back down. So UV can sometimes be in that realm as well. Sometimes it's not, but sometimes it is. So on your sheet, again, I would encourage you to look at microwave versus infrared versus UV when you get a chance to remind yourself of those three things. That's something that I've seen more recently on their practice tests. I want to make sure that we are aware of that as well.